Okay, inverse matrix 2.2. Uh, mm, okay. So here's the definitions. A matrix A, okay. A matrix A is said to be oh, sorry. As inverse matrix is, let me use B, okay. Sorry. Is an inverse matrix. Okay. Inverse matrix of matrix B if B times A is equal to identity matrix, and A times B also equals I. So simply saying that A times B is equal to B times A is equal to I. Okay, this is called the inverse. In this case, B is the inverse matrix of A. Okay, and then also inverse matrix of B is A too. So A and B are inverse matrices each other, actually. So when you want to find out inverse matrix of matrix A, then you got to find out matrix whose multiplication of A return identity matrix. I is an identity matrix. You know, identity matrix, remember that? I is something like this. All the diagonal entry is 1, and the other entry is 0. So this is identity matrix. Okay. So one thing that I didn't mention that in 2.1, matrix multiplication will not satisfy commutative property. So when you do matrix multiplication AB and you change it, the order or the change order, that will not return the same result of the AB in general. Okay. So keep in mind, right there, AB is not equal to BA in general. Why does it matter in general? In general means what? In particular case, there exists something special matrix that AB makes the AB equals BA. Okay. But in general, AB is not equal to BA. Keep in mind this. So then in inverse matrices, so AB equals BA, but especially they will return the identity matrix. Okay. Okay, so now then next one, see definition, other definitions, because we don't have time. So A matrix, A is said to be singular. Or non-innover. Okay. If it is not square or A inverse does not exist. So keep in mind this, when you're talking about the inverse matrix, we assume that matrix is square. Okay, so here, oh, sorry, assumptions, big assumptions. A and B too, okay? A is a square matrix. Okay. A is a square matrix. So we're only talking about square matrix. Under that assumption, we're talking about inverse matrix. So matrix A is said to be singular or non-innover if it is not square or A inverse does not exist. Okay. So otherwise, it is called a non-singular or invertible. Sorry. Otherwise, it is called non-singular. Then or here singular non invertible. Sorry. Sorry, it's not invertible, non-singular, or invertible. Okay. So here's the theorems. I think you know about this. Theorem 2.4 in section 2.2. So if matrix A is A, B, C, D, okay, it's a 2 by 2 square matrix. Okay. So and then with DETA, so we're talking about this one in chapter 3. Okay, that means the determinant of matrix A. Okay, this is called determinant. A is denoted by, defined by AD minus BC. This is not equals 0. Okay. Then especially, yeah, so here you can see that the in theorem 2.4 is talking about the inverse matrix of 2 by 2 matrix. That was already formalized. Is given by this A inverse is 1 over determinant of A times, and then now what are you going to do? We change it, listen carefully. We change A and diagonal entry A and D. It's a D. Okay, is a D and A. We change the diagonal entry. Okay. And then we put the negative sign in the other entry. Okay, so this is going to be minus C and then minus B. Okay. They already figured out the inverse matrix of 2 by 2 matrix is like this. This is more kind of formula. Okay. So you better just memorize this. It's sometimes useful. D minus B minus C and A. Okay. So 3 by 3 matrix also there is a formula. So I'm not going to cover that. Okay, but you can find out in you can just Google it. You can easily figure out. Okay. So theorem 2.5. So there's an example, but let me skip it. Okay, but please look at the example in your textbook. Okay, so let me skip it because theorem 2.5 is quite uh this one of the main part in 2.2. Okay, so if A is an invertible matrix, so means that matrix A has inverse matrix. Invertible, n by n, yeah, definitely, because it should be square matrix. Okay. So then for each B bar, this is really important. This one give us the reason why we have to find the inverse matrix. Why that matter? B bar in our n space. And the equation, A x bar is equal to B bar has the unique solution. Okay. X unique solution, x bar is equal to actually A inverse B bar. Okay. Before we prove this, look at this. A is invertible. Then for any B bar, we can then there exists the unique solution. This is not only exists solution, but also that solution unique, which is this. What that means? Think about this. In chapter 1, what we did for given matrix B, we construct the augmented matrix, right? And then we do echelon form, row reduce to get the echelon form or reduce echelon form. Whenever B bar is given, which means that B bar is changed, we have to newly construct the augmented matrix for each matrix B. Whenever B bar is different, we newly construct the augmented matrix and then we do echelon form. But now here, this one tells us that what? For any choice of B bar, it doesn't matter. As long as we can find A inverse, X bar is just multiply inverse matrix with B bar. That's it. So it's much easier to find our solution. And that solution is also unique. We don't have the construct the augmented matrix and over whenever B bar is changed or given differently. So so that's why the every most of mathematicians want to find out A inverse. Okay, efficiently, effectively actually. Okay, but here's a question then: how can you guarantee that the matrix has inverse matrix? That's other issue too. Okay, we need to show that we need to figure out existence of matrix, inverse matrix. Sometimes the matrix does not exist inverse matrix. That's called the what? Singular matrix, right? But think about this. Data is given everywhere, right? So for the given data in a nature or social science, whatever, engineering or other field, so we collect the data and then the using that data to use that data as a tool, we reconstruct this one as a matrix. Pretty much we got the matrix from the nowhere. Then we need to figure out this matrix is singular or non-singular. That's a big issue, actually. That's the other the research field. Okay. So this one, here's a proof. Proof is really simple. Okay. So let's say B bar is in Rn space. Yeah, it should be. Okay. So we're gonna show that it exists because this one has a unique solution, right? To show the uniqueness, we have to show the existence first and then uniqueness. So here's strategy. First one is existence. Okay. So B and then show that the solution exists on solution. Okay. And then we show that the existence of a solution. So let's say X bar is A inverse and then B bar. Okay. So keep in mind this. What's the assumptions? When you prove a theorem, you gotta just take advantage of the assumption of theorem. With theorem is always consist of the assumptions. It's called the hypothesis, okay? Assumptions and conclusions. So right now, this is assumption, right? Let me say use a hypothesis, okay? Hypotenuse. Okay. And then let me use other color, maybe blue. Okay. So this one, including this one, and this one is conclusion, right? We're gonna show this using that hypothesis. Okay. So since the A is invertible, which means that there exists A inverse, that's why we can say X bar is equal to A inverse times B bar. We can use A inverse because there exists A inverse. This is what they said in theorem. Okay. And then AX bar is equal to A times, because we just substitute. Okay, in Korean, substitute means they. Okay, we substitute this one into the X bar. So it is A inverse, right? And then a B bar. This is going to be what? A times A inverse what? Identity matrix. So we got I B bar, which is what? B bar. Because identity matrix times whatever matrix is this matrix itself. Thus, a solution exists. Okay, next we show that the uniqueness. So now next one, we show the uniqueness. Okay, uniqueness of the solution. Okay, so here's a strategy. It's a really general way to do to show that the uniqueness. Let's say there exists another solution. Okay, that's a really traditional way. Okay, let's say if y bar, let's say y bar is the another solution. Okay, so then a y bar, because y bar is a solution, then a y bar must return the b bar, right? It must be. It should be. Okay, and then multiply the both sides by a inverse. Okay, and we obtain. So multiplying both sides by A inverse, what happened? Let's see. A inverse times A y bar, right? That's the left-hand side. And the right-hand side is going to be A inverse and then A inverse and a B. Okay. So now then what? This is, if and only equivalent. This means equivalent, or if and only equivalent to this I y bar. Why? Because A inverse times A is what? Identity matrix. That's the definition of inverse matrix, right? So that's why we got I y bar in the left-hand side, and the right-hand side is A inverse B. Okay, so this is equivalent to y bar, because I y bar is this y bar, because identity matrix just literally do nothing. So y bar is A inverse B bar. But what is this? This is equal to what? Look at the conclusion of the theorem 2.5. X bar is A inverse B bar. So this is exactly the same as what? X bar. So we got this. X bar is equal to Y bar. Thus, the system has unique solution. So we assume that what? We start from the another solution Y bar. So we derive it. It turns out that X bar equals Y bar. So there is only one solution. So thus the system has unique solution. Okay, the system unique solution. So yeah, okay, that's for today. So give me a second.